The extraction and refinement of petroleum to produce synthetic plastics and synthetic leather leaves behind a massive environmental footprint. The resulting materials are entirely non-biodegradable, compounding an already critical global waste management crisis. A highly scalable, biocompatible alternative is found in fungi, specifically fungi belonging to the order Polyporales. The viability of this alternative comes down to structural homology. The vegetative part of the fungus, called mycelium, relies on a strong cell wall built from chitin. Because fungal chitin is structurally similar to the cellulose found in plants, the two materials can bond tightly together. When fungal hyphae are introduced to agricultural waste, they metabolize the nutrients and colonize the biomass. They form dense, three-dimensional filamentous linkages that bind the organic material into a unified biocomposite, resulting in materials like mycelium leather, often referred to as mylia. Moving this material from a laboratory theory to an industrial-scale substitute requires actively engineering the organism's environment to maximize its yield. The successful biofabrication of mycelium leather relies entirely on producing a perfectly engineered precursor, the mycelial mat. This mat is a dense, tightly woven network of hyphae that serves as the primary structural foundation for the final composite material. Scaling this precursor depends on maximizing radial growth kinetics. The faster and denser the mycelium spreads, the faster the mat can be harvested. This rate of growth is dictated by a specific set of variables: the biological isolate selected, the baseline culture media, the ambient temperature, the pH level, and the physical substrate composition. By analyzing the kinetic data across these variables, we can determine the exact bioreactor parameters required to produce the maximum material yield. The evaluation begins with 4 distinct isolates from the Polyporales order: Ganoderma, Trametes, Polyporus, and Hexagonia. To establish a baseline for growth, these isolates were cultured in dark conditions for 5 days across 4 different nutrient media formulas. This chart compares radial growth on 4 nutrient media. Potato dextrose agar, or PDA, universally outperforms the rest. On PDA, Ganoderma and Polyporus demonstrate superior growth, expanding over 11 millimeters per day. Trametes and Hexagonia show significantly lower outputs and are eliminated. Ganoderma and Polyporus, cultivated on a PDA baseline, remain the optimal biological starting agents. Now we begin tuning the abiotic parameters. Temperature is a primary abiotic controller. It directly dictates the physical morphology of the fungal cells and regulates their enzymatic activity. This chart tracks a